Let me share the slide. Okay. Okay. Can you see my slides? Can you hear me? Am I online?
Yes, Professor.
Yes,
Very good.
Professor.
Excellent. Excellent. So today we're going to essentially, let me get the pointer here, finish up with a little review. Again, I will go fast, but I will try and emphasize a few things that we're going to need in the future, near-term future. So eventually we want to go back, and perhaps I'll start today dealing with crystals, having finished to review what I wanted to, to make it clear so that we can proceed. Um, and and so we're going to get to the definition of a crystal, hopefully at the end of this lecture, and that's where we'll start building one of the main topic of this class. I remind you here, for those who were not here last time, an outline of what the class will be. Again, the main chunks will be the calculation of the call it band structure, the excitation spectrum of a solid, and eventually dealing with excitations around about from the ground state of the system, which are the essentially physical processes which determine scattering of electrons in a solid, and then we'll move to the dealing with the theory and then calculation of the electronic transport properties, so charge transport in a solid. I'll remind you about the text as I recommended. So last time we saw again a little bit of the foundations of quantum mechanics, canonical quantization, having reformulated our physical system first classically in terms of Lagrangian and Hamiltonian formalism, how we quantize a general system. So far, we have restricted our attention to a system which has a finite number of degrees of freedom, as many as you wish, but still finite. And eventually, in order to deal with elementary excitations of solids, phonons, for example, or even if we quantize an electromagnetic field in vacuum, still we will need to quantize a field. So we will extend that procedure, the procedure that we showed last time, we'll extend it to this more general situation, which is a little more cumbersome, but in a way, I hope I will convince you later on that it's actually simpler from an algebraic point of view than dealing with quantum mechanics and partial differential equations. So today I want to go into the next step, which is remind you a little bit about how we build a periodic table, not so much because I assume that you know that already what it is and how we build it, but I want to emphasize one particular aspect of what happens when we move from Schrödinger equation for a single electron, which is, for example, what you do with a single particle in a box, or the hydrogen atom, in which you have, assuming that the nucleus is fixed because its mass is so much larger than the electron mass. So we have essentially a two-body problem that we reformulate in one particle formulation. As soon as we move to two electrons, so the helium atom, there are some complications, which are some complications that we will, of course, see again when we deal with many electrons, even more complicated. So I want to make a little bit the physics clear about what happens when we deal with two electrons. So let me go fast here. Again, I go fast because I assume that you've already seen this stuff. However, please feel free to interrupt me anytime if you would like me to stop, to pause, to explain a little bit more what we're doing here. Again, I'm going fast because I think you know very well what's going on here. So you go usually when you take an introductory course in quantum mechanics, you start dealing with a free electron, with a particle in a box, in a one-dimensional potential. Then you move to three dimensions. In one dimension, you know already that the spectrum of the Hamiltonian, which determines how many states you have, can be a continuum. If you have a particle, for example, an electron in a constant potential, can be discrete, fully discrete. if you deal with a particle in a box which has infinitely high walls, so an infinite potential that confines the electron into a particular finite domain in one dimension. You may have a combination of a discrete and a continuum spectrum. The continuum spectrum may be doubly degenerate, particles which are moving left and right, can be not double degenerate, just a single state per number. In any case, you need a single quantum number because you are in one dimension. Each quantum number essentially represents the number of degrees of freedom that you have. If you move to a particle in 3 dimensions, you know already that we can follow the usual procedure. We are Schrödinger equation now in 3 dimensions, written down explicitly, it takes this form. We have 3 degrees of freedom, of course, the 3 possible directions in which the particle can move. We do separation of variables the usual way. So we assume that the wave function, which is function of x, y, z, is the product of 3 functions, each of them function of 1 independent variable. Again, the general solution is not necessarily of this form. It depends on the boundary conditions that you set, but in general, the solution will be given by linear superposition of functions of this form, so it may not be at the end separable anymore. And you can combine these linearly because Schrödinger equation is a linear differential equation, partial but linear. So we need 3 quantum numbers now. Indeed, if you separate variables, you can re-express your Schrödinger equation into pieces in which you have total derivatives only with respect to one of the 3 variables. And then following the usual procedure, you divide by this expression by the wave function, say x or y, say z. So you find that your equation, differential equations, has on the left-hand side a sum of 3 terms, each of them depending on only one independent variable, which means that each of them have to be equal to a constant separately, and the sum of the 3 constants must be equal to the energy of the system, of the particle that you have. So you're left with 3 ordinary differential equations, not partial anymore, still linear, second order, everything is fine. And you know that the solution of these equations is the harmonic oscillator, essentially. So it has to have a form of exponentials, okay? And then you can combine finally your solution. Remember, we expressed it in terms of a product of these 3 functions. Each of these functions has to have the form of an exponential. The sum of the square of these numbers has to be equal to whatever we have on the right-hand side of this equation. And so you can express finally your solution as a plane wave. I hope that this is clear to everyone. Again, interrupt me if it's not clear. This is now a k-vector. The k-vector is a combination S vector whose components are the wave numbers along each direction, and each wave number is formulated in terms of the energy, so to speak, along that direction. Ex plus Ey plus Ez will be the total energy, and we can represent our wave function in this form. And then, of course, we can form packets, we can add them linearly depending on the boundary conditions that we have. For example, if the boundary conditions are different, we know that these numbers now, these wave numbers, have to be a discrete multiple of the pi times divided by the length of the side of the box, if we're the particle in a box. This is something that we will use also in the future when we'll deal with crystals and so on. Usually you can normalize wave functions or assume that your system is a finite system. And this is what we usually will call the finite volume normalization, in which the wave functions will be assumed to be periodic, or maybe with Dirichlet zero boundary condition at the edges. It doesn't make much of a difference. And this will be the finite volume normalization. And then we will see how to convert it into a delta normalization or infinite volume normalization, when we'll assume instead that the wave functions are defined over the entire real axis or the real space in 3 dimensions. Again, I hope that this is clear. So if we assume now that the particle is in a box, we have Dirichlet boundary conditions. By the way, I see Dirichlet, say Dirichlet, not Dirichlet. He was German, so it depends perhaps on which side of Germany you are from. Maybe from the south in Bavaria, you would say Dirichlet. You can say it any way you want. I don't know what he would have said, how he would have pronounced his name. Anyway, so the particle now has, again, we have three quantum numbers because we have a particle in 3 dimensions. So we need 3 quantum numbers, and the total energy can be represented as a combination, as you see here, of these 3 quantum numbers. This is again the fact that we're normalizing the wave function to the volume, the finite volume. Again, now we move to the hydrogen atom. I want to deal briefly with this. Again, I assume that you've seen it many times before. We follow exactly the same procedure that we followed now for the particle in a box. The potential now is not flat. The boundary conditions will be different. Will require the wave functions to go to 0 at infinity. And that's because the total probability that the electron is anywhere has to be 1, depending on how you normalize it. But in general, that's what we require. This actually is required to make the Hamiltonian, the Laplacian, if you want, a bound operator. If you don't impose this boundary condition, then the operator becomes unbound, and then all sorts of problems come up. So this is a physical, but also a mathematical constraint that we require. So now the situation is similar, except that since the potential that we're dealing is the Coulomb potential, which is of course spherically symmetric, it makes sense to use a system of coordinates, the polar system coordinates, in which we exploit explicitly this symmetry of the problem, which is related somehow to what I said last time about the original intent of those who formulated Lagrangian and Hamiltonian mechanics. It was just to exploit and take benefit from the various possible symmetry of the problems that you're dealing with. So now we do exactly the same thing, except that rather than separating into Cartesian coordinates, we separate it into polar coordinates. So our wave function for the hydrogen atom will be the product of a function which depends on the radial coordinate, how far you are from the nucleus, and then from the polar and the azimuthal angles that are the two other canonical variables, if you want, that we have to use. So we are showing your equation in this form. We can proceed many ways. I'm sure that you've seen it before. If you express the Laplacian into polar coordinates, you get some nice expression. Our Schrödinger equation now becomes essentially what it is, the Laplacian, the angular part of the Laplacian, and then there is a radial derivative, of course. If you plug our assumption that the wave function is separated into 3 functions, each function of only one independent coordinate variable, we insert it here, and then we can use exactly the same procedure, more complicated algebraically, simply because the Laplacian in polar coordinates is quite a bit messy, and you find that you end up with 2 equations. Again, I hope that this is well-known stuff, in which we separate an equation which is a function only of the angular part, which as I show here, and one is function only of the radial part. Here it's a first step in doing this. We separate only a component which depends on the azimuthal angle. This has to be equal to a constant, because this is a function only of the azimuthal angle. This is a function of the radial coordinate and of the polar angle. So they both have to be equal to a constant. We call this constant some m squared. We want it to be positive. If it's negative, it doesn't work, because it would tell us that the angular component of the wave function will explode exponentially with the angle phi. And then by physical arguments, also mathematical if you wish, the fact that this function has to be single valued. So if we rotate the function by 2 pi, we should come back to where we were. This m squared actually has to be the square of an integer. And this is the usual story. It's boundary conditions that determine the fact that you have discrete quantum numbers. Okay, you plug it back in, and then you can proceed as usual. Now that you know what the solution of the one angular part is, you can plug it back, and then you can separate the equation into something that depends only on the radial coordinate, something else that depends only on the polar angle. You proceed as usual, and I hope that you're familiar now with what you're going to get. The angular part was actually the square of the angular momentum operator. So the eigenfunctions, we know what they are. They are the spherical harmonics, which are expressed in terms of those exponentials that we saw before for the azimuthal part. And then we have the associated Legendre polynomials, for the polar angle. And another set of polynomials will come up will be for the radial part, and those will be the Laguerre polynomials. I will not go into deeper detail here. There is the other way to go into deriving the solution for the angular part by looking at the angular momentum in quantum mechanics. We will see it later, so I'm not going to discuss it now. Excuse me, bad weather here. If you have never seen this, let me know. We may have to discuss it. I know it's not easy. I know I'm going fast. So please let me know, okay, if this is not clear or if you have not seen it before. There is always the risk of either boring people by repeating what they know already or going too fast and saying something that remains obscure. So I will not say any more about this. I remind you again, we have now 3 quantum numbers because we have 3 degrees of freedom. The 2 angular momentum quantum numbers, usually the number L, which is the total angular momentum related to the square of the total angular momentum. The quantum number little m, which is the projection of the angular momentum along the z-axis by convention. And then we have another quantum number, which is coming from the Laguerre polynomials, which is called sometimes the principal quantum number. It's the radial quantum number. It's essentially the number that says how many nodes in a radial direction your wave function will have. So we recover a situation which is conceptually similar to the particle in a box, very simple, except that it has become algebraically more complicated, I would say calculus-wise, more complicated because of the fact that the potential is not flat. So we're dealing with these strange orthogonal polynomials left and right. Good, so we know what the states of an electron are in the presence of the Coulomb potential due to a nucleus. That's my hydrogen nucleus. We have these 3 numbers, the number n, the number L that can go up to n-1, and then the number n that can span, since it's a projection of the angular momentum on the z-axis, quantized. It can go between being totally down or totally up in steps of an integer. And of course, the angular momentum will be given by these integers multiplied by h bar for the right dimensions. Now, if we go and build the periodic table, you know very well what happens. Historically, I'm not sure how it went, but first of all, you need to introduce another quantum number, which is related to an internal degree of freedom of the electron. That this was introduced ad hoc. So maybe at some point, if you would be interested, we can see how another quantum number comes up, spin, comes up automatically if you formulate your differential equation, your Schrödinger equation in a relativistic way. And we can discuss a little bit, and if you wish, let me know. We can talk about how you can derive an equation for a single electron, which is a wave equation for a single electron, which is covariant under relativistic transformations of coordinates. And that is either the Klein-Gordon equation, which actually has lots of problems, or what was one of the major accomplishments by Paul Dirac was the Dirac equation. And that has the major advantage of introducing spin automatically. Spin comes up without having to be introduced ad hoc. Instead, historically, before the Dirac equation was proposed, invented, discovered, we can discuss about philosophy of knowledge, what is the right term to do it. I would say invented. Before that happened, people were a little puzzled. They realized that we're missing a degree of freedom. There was some experimental evidence that actually an electron had a magnetic moment. We'll talk more about this dealing with spin-orbit interaction. And then so this magnetic moment has to come up from some internal degree of freedom of the electron, internal motion of the electron, if you wish, which semi-classically we can view as an electron rotating over one axis along one direction, taken as the z direction arbitrarily. In addition, you needed to make another ad hoc hypothesis, which was two electrons cannot occupy the same state. So they cannot have, if you have two electrons, they cannot both have the same set of 4 quantum numbers, which are the 3 quantum numbers that are related to the degrees of freedom of motion in real space, so NLM. In addition, there is this quantum number S, which is spin, which can take a value plus or minus a half for the electrons. And Pauli suggested that you cannot have 2 electrons which share the same set of 4 quantum numbers. And then you can build your periodic table. I want to discuss a little bit that actually there is a little bit more than that, and we'll have to deal with this. So you have problems dealing with many electron systems. And the problems are essentially 2. One is clear, I think. If you consider the helium atom, which is the first next step. So in a hydrogen atom, you have the electron that feels the potential of the nucleus. Good. It's just a central force, no problem with that. If you add a second electron, you immediately see that you have some issues. One electron feels the potential of the other, but the other electron, of course, feels the potential of the first electron. So we have to do something self-consistently here. So we can start numerically, for example, we can solve the problem by first finding the wave functions of the electrons which are assumed not to see each other. So essentially we do exactly the same wave functions that we find for the hydrogen atom, except that the charge of the nucleus now will be twice as large. We find these wave functions. Now we calculate the charge of each electron by taking the square of the wave function associated to an electron in a ground state. We add it to the Coulomb potential, and then we solve again the problem for the other electron. So we find new wave functions, which now feel the potential due to the charge of the other electron to some extent in this first approximation. These new wave functions can be used to calculate a new charge density, which is corrected now to the second order, and we keep going by this iteration. And this is essentially what is called the Hartree mean field approximation. For a two-particle system, perhaps the mean field is kind of a misleading thing, but we look at one electron as feeling the potential of the other electron, time averaged, and without any fluctuations around it. If we were to deal with beryllium, now we have another 2 electrons in addition to our electron. So we look at the potential that the first electron feels due to the wave function of the first electron when calculating, solving Schrödinger equation, adding the potential of the other 2 electrons. And we can iterate in that way. Of course, things get complicated. This will be a good thing to do, and indeed that was the first thing that one can try, is the Hartree energy, sometimes called the additional energy that you have in addition to the energy caused by the interaction with the nucleus. Very nice, except that it doesn't work. It misses the prediction of the spectrum, which is observed experimentally, of many electron atoms by quite a bit. I think almost a factor of 2. So what are we missing? We're missing something which actually is implicit in what Pauli had to say. The reason why 2 electrons cannot occupy the same state, cannot share the same set of 4 quantum numbers that we have, is due essentially to something which is called the spin statistics theorem. If you go to, I think you have to invoke Lie groups, I may be wrong here, but the generating function for rotations. You find that actually, if you rotate the system by an angle phi, any physical system, but let's consider just the one particle wave function, okay? So we have a single particle, a single electron, and we rotate it by an angle phi. The rotation, actually, you would say, well, I rotate it as a cosine and sine, and I'm done. Actually, by group theory, it turns out that the spin of the particle has something to do with it. And you change the phase of the wave function by an angle which is s times phi. If the spin is an integer, is 1, we're dealing, for example, with a photon, good. That's the usual intuitive thing. If the spin is half integer, 1/2 for our electron, then we see something strange. Rotating the wave function by an angle phi, if we want to go back exactly to where we started from, we have to rotate it not by 360 degrees, but by 720. We have to go around twice. And that's because the spin is half integer. And that is the result of group theory. So if we consider now a 2-electron system, so we have a wave function of 2 coordinates of the electrons, let me assume that it's a product of the 2, which is what is called a single particle picture. We'll deal with it later on when we'll have to deal with many electrons, very many electrons. But let me make this simple assumption. By the way, this argument is very simple, very clear, but very wrong. Anyway, it gives the idea, so I'm going to use it anyway. So we have to rotate the 2 wave functions. Each of them we rotated by an angle phi. So the total thing is we rotate the wave function by an angle of 2 phi, or to go back to where we were, except that there is the spin here of each particle, which is 1/2. So if we rotate it by pi, which 180 degrees, right, which means that we have swapped particle 1 with particle 2, because we're just rotating it by 180 degrees, so we're swapping the position of particle 1 with particle 2, you see that we get a minus sign because of this strange factor here. We don't get e to the 2 pi, which is what we would like to have, right? But we get a rotation of 180 degrees, which is the minus sign. Which means that by flipping the position, swapping the position of particle 1 with particle 2, we have gained a strange minus sign, which means that the wave function of 2 electrons, in general, of any number of particles with half integer spin, has to be antisymmetric when I swap 2 particles, the indices or the positions, if you wish, of the 2 particles. This is where Pauli's principle comes from, right? The reason why this is true is deeper than the simple argument that I gave you. And later on, I will mention the spin statistics theorem. I will not be able to prove it because it's an extremely complicated thing. There is an entire book to prove it. It depends on some axioms that you use in quantum field theory, locality, causality, relativistic covariance. You need all of these axioms in order to prove it. And the general statement is that half integer spin particles have to have wave functions which are antisymmetric. Equivalently, we remember that we talked about canonical commutation or canonical anti-commutation rules yesterday. For half integer spins, those famous canonical commutation rules, the Poisson bracket between the P and the Q, they will have to be converted into anti-commutators for half integer spin particles. So they're all linked together. Good, so we'll talk more about this, but for now, the major thing is that if I take 2 particles, let me ignore the presence of spin for now, that complicates things. But if I have now 2 particles which are in an antisymmetric state, it's relatively easy to see that the average distance, the expectation value, if you wish, of the distance between 2 particles, so you take an antisymmetric wave function and then you compute the expectation value of R1 minus R2, its absolute value. You see that it is bigger than the value, the expectation value that you would have if instead I were to assume that the wave function is symmetric. This will happen when the spin S. Is there any question? I hear some noises. Questions? No? If you have a question, please say it clearly. I'm not sure. Okay. Anyway, so if I have instead an integer spin, then you see that I get a plus sign. So this will be symmetric. And you can calculate the expectation value of the distance between the 2 particles when the wave functions are symmetric, and you see that it's much closer, much smaller. I may give you an exercise if you wish, but it would be good, for example, to consider a particle in a box. You consider 2 electrons in a box now, and you consider a wave function which is the symmetric combination of the various signs that you have for the particle in the box, or you consider the antisymmetric. And then you calculate the expectation value of the average distance between the 2 particles. Do it in 1 dimension, that's enough. And you will see that if you symmetrize, this number is smaller. If you anti-symmetrize, it's bigger. If you don't symmetrize anything, so you leave just a product of the wave function, you get something in between. Why does it matter? It matters because if these particles are charged, when you take them closer together, which happens when the wave function is symmetric, bosons, integer spin particles, or if you take it instead when the two particles are have integer spins, so the wave function is antisymmetric, their distance is bigger, so the Coulomb repulsion of two integer spin particles will be reduced with respect to the two particles which are instead integer spin, two bosons. And this change in energy, it's called the exchange energy. It's not directly related to the fact that the particles are in a symmetric or antisymmetric state. But when you have particles which are charged or they interact somehow in some other fashion, for example, in ferromagnets, then this exchange energy becomes extremely important. And in a two-electron system, the helium atom, for example, a many-electron system, you can actually go beyond the simple mean field of self-consistent field approximation, the Hartree approximation, and this is what's called the Hartree-Fock approximation, in which you account for the fact that the particles have spin, and so they can be in either a symmetric or an antisymmetric state with respect to the spatial coordinates. That gets a little iffy. We'll talk a little bit more about it. Remember, I've ignored spin here. The wave function also has a component related to spin, so we can symmetrize the spin component and anti-symmetrize the spatial component, or vice versa. So we're dealing with singlet or triplet spin states, and they interact differently, so their exchange energy is different. But the overall effect is that the Coulomb repulsion is reduced tremendously. And this is why the Hartree model, the Hartree approximation, gave you wrong results. By the way, in ferromagnets, they have an ampere number of electrons in the outer shell, so they have, I'm sorry, I have a message which says that I have bad network connectivity. Do you still hear me? Am I online?
Yes,
Yes,
Professor, we can hear you, but sometimes the audio cuts.
Am I breaking up maybe?
Yeah, you are breaking out times.
Okay, if I break up, if I lose you, let me know, please. Okay. Okay, let me go back. So is my slide visible still? Am I still okay? Yes?
Yes, Prof.
Good, excellent. So for ferromagnets, I was saying, it's very important because you cannot have two magnetic moments aligned in the same direction. Their energy is high, right? They repel. So you would like to flip them. So how come that some of these electrons line up instead with parallel magnetic moments, as in is a magnet, the magnet, a regular magnet? And the reason is that actually when you have electrons which have spin which are parallel, their wave function is antisymmetric in a spatial direction, and their Coulomb repulsion is reduced dramatically more than the increase in energy that you get from the repulsion between the two parallel magnetic moments. So without the exchange energy, you could not explain why you have magnets. So this is extremely important, and we will deal with it, and it's one actually of the major issues in calculating the band structure of solids. Just to complete the story, we're not quite done yet. Hartree-Fock works much better than Hartree. Work much better means it predicts a spectrum for the helium atom or beryllium and so on, which is in much closer agreement with the experiments than the Hartree model, but it's not quite there yet, especially for many electron systems. And there is something missing. The term for what's missing is usually correlation, the correlation energy. Electrons find a way to distribute themselves in a way that minimizes the total energy a little bit more than what you would have by the reduced repulsion, Coulomb repulsion caused by the exchange energy. The only correct definition of correlation energy I can give you is it's the difference between what I should be able to calculate and what I can calculate, okay? So it's an extremely messy situation. As far as I know, the exact formulation has been given by Kellman and Bruckner. using sophisticated diagrammatic techniques, whatever, for the homogeneous electron gas. In general, you can use now Green's function technique, so-called GW method, that helps a little bit, but it's always a spiny, very spiny issue. Okay, so we'll talk more about this in dealing with the band structure. So this is the important step. Going back to the first slide, I said, yeah, you can build a periodic table. We know how to build it. You need Pauli's help in terms of knowing that spin exists and that two electrons cannot occupy the same set of quantum numbers. And so at most you can have, for a given set of 3 quantum numbers, N, L, and M, you can have 2 electrons because they can differ in spin, one spin up, one spin down, but no more than 2. The reason why this is so, historically, actually I'm not totally sure, but I think it was a little bit ad hoc, seeing that if you make these assumptions, then you explain the periodic table. But the deeper meaning of the spin statistics theorem was yet to be determined. I think that the book in which it was proven by Streeter and Whiteman came out in the 60s. At least the book is a Benjamin book, 1962 or 64, I forget. So it was some 30 years, 25 years at least, after this thing was developed, the periodic table. So you can start building your periodic table. I'm not going to spend too much time. You know, hopefully the notation that we typically use. For example, for carbon, you will use this notation for the electronic configuration. S is SP, D, F, and so on. They labeled the angular momentum states. Historically, I think S for the L equals 0 states comes for sharp because the spectral lines were very sharp. The P was for principal. The D for diffuse, the F for fundamental, then they run out of terms, and then from there on you run alphabetically. Anyway, they determine the quantum number L. The first number is the principal or radial quantum number. The little superscript here says how many electrons you have in each of these states. So we'll be interested, for example, I think I have it here, in silicon, which has a total of 13 electrons, and they are arranged in this configuration. Germanium, it's exactly the same outer configuration, 4 electrons in the outer shell, 3 for silicon, 4 for germanium. Carbon, silicon, germanium, what comes next? Lead, what is it? Antimony then, and then, no, antimony is group 5. They are all share the same outer shell configuration of 4 electrons in the SP outer shell. And of course, in device physics, particularly for high frequency, people use the so-called 3-5 compound semiconductors, which are essentially, they give you the same crystal structure of silicon, germanium, carbon, and so on. Tin was, sorry, in the group 4, tin before lead. And then there's flerovium, I guess, which is a transuranic. But anyway, so what you do if you combine a group 3 with a group 5, by the way, by group here I'm meaning the physics, the physicist terminology, not the chemist, that they go up to 14 or whatever. So essentially you recover the situation that you have for silicon and germanium, because combining 3 with one group 5 element, you get a total of 8 electrons shared by a bond which is not covalent strictly anymore, but it's also ionic. So they have the same crystal structure, which is a face center cubic structure, and similar electronic properties. So we'll talk more about that. Good. Just to remind you, again, here I'm going to go relatively quickly because I want to get to crystals finally. You can combine the electrons and molecules. Just to review briefly what kind of bonds you can have. If you take 2 atoms and bring them together, several things can happen. The first thing is nothing happens. For example, if you bring 2 elements of the 8th column of the periodic table together, nothing happens. They are inert. So 2 neon atoms, they don't do anything. You can instead form ionic bonds. If you take an element from the far left of the periodic table and combine it with an element of the far right, you get a charge transfer. Typical example is kitchen salt, sodium chloride. You take an electron for the sodium, which has a lone electrons in the outer shell. You give it to chlorine that really would like to have 8 electrons in the outer shell, and you form a strong ionic bond. If you take two elements which are in the middle of the periodic table, group 4, like silicon, like carbon, like germanium, they instead share the outer electrons in the two outer shells, so forming complete shells when they share it, share these electrons. And there's no much of a charge transfer in this case. It's you form a covalent bond. Of course, there is something in between. So if you take sodium and chlorine, clearly you get a purely ionic bond. If you take two silicon atoms, clearly you get a covalent bond. If you take gallium and arsenic, like gallium arsenide, you have a mix. It's a bond which is covalent because some electrons are shared, but you also have such charge transfer. Not complete, but you have such charge transfer. So there is a component of ionicity in the bond. If you consider instead metals, say aluminum, you have a cubic crystal in which the aluminum ions occupy sites in this cubic crystal, and then they share electrons everywhere. So it's neither covalent nor ionic. All the ions are ionized. Well, of course, but well, the atoms, I should say, are ionized, but the electrons are shared uniformly. You can assign one electron to an atom or a pair of atoms, and this is the metallic bond. Then there is something that I think Phil Anderson called one of the big mysteries of nature, the hydrogen bond, in which this is what I think links the various groups in DNA molecules, the bases, the biological bases, C, G, T, A, whatever. And it's a little bit, I think there's been some progress, but I would add, together with the hydrogen bond, which is kind of still mysterious, I think the hydrogen is a problem by itself, together with oxygen. Indeed, water is one of the less understood, I shouldn't say solid, amorphous material, liquid that we have. And I think there is a lot of work, and I was a couple of years ago at a conference where they had an entire group discussing DFT calculations of water. So it's a major issue. And then something which is of interest today because of graphene and the popularity that all 2D materials, two-dimensional materials have had, is the van der Waals forces, in which essentially you rely on two materials which are in close contact together. They polarize each other in a dynamic way, so these plus or minus charges keep oscillating at some frequency, and it's indeed what connects a sheet of graphene to the next sheet and what makes your pencil work. When you strike your pencil on a piece of paper, you essentially exfoliate a layer of graphene out of the graphite, and that's because the van der Waals force is relatively weak, and then by the same force it sticks to the paper. So it's a dynamic, if you want, polarization-induced electrostatic force. Okay, one final thing, because that is what we will extend to the band structure of the solids. If you take two atoms together, so they have some wave functions in the outer shell, this is just a cartoon to show the idea. When you pick the two atoms and you bring them together, excuse me, the wave functions of one atom and the wave function of the other atom can be combined into a linear superposition. And of course, you have the choice to combine them by adding them up in phase or subtracting one from the other, so adding them out of phase. In general, what you have is that you build charge, as you see here, between the two atoms, and this contributes to the bond. So you have electrons which are shared by the two atoms, and in this in-phase superposition of the two states, you build what are called the bonding states. They will become the valence bands in crystals. So in a molecule, so in H2 molecules, in a hydrogen molecule, this will be the bonding state. And it's just the take your electron, the 1s wave function of electron of hydrogen 1, the 1s electron wave functions on hydrogen 2, you add them up together this way. You can also add them in the other way, as I said, out of phase, in which case you have a zero charge between, in this simple picture, you have zero charge between the two atoms. So they don't contribute to the bonding of the two atoms. And they eventually will become the conduction bands in a solid. So let's keep this in mind when we we'll refer to bonding or anti-bonding states or wave functions or whatever. This is what we mean. If you have graphene in mind, this is the typical pi band that you have in graphene in a conduction band, which is an anti-bonding state. Good. Any questions so far? This concludes the review. So if you are okay with what I said, by okay, I mean if you got bored and said, well, I'm not learning much in this class, then it's good, because that's what I hope is the background that we all have. If there is something that you didn't know, well, good. If there are a few things that I hope perhaps you didn't know, if there are a few things, okay, but if you got lost somewhere, please let me know. If you're shy here online, send me an email, contact me some other way, by Teams, send me a message on Teams or whatever. But from now on, I think we're going to deal with something which is different, and maybe not all of you have seen it, which is related to solid-state physics. So if there are no questions up to this point, let's get into crystals. If I hear any objection, no objection? Okay, then let's start with defining the crystal. So the idea now will be define what crystals are, and then we'll have to go into a part of the class that I really like, but it's kind of challenging culturally from a conceptual point of view. We'll have to deal with the total crystal Hamiltonian. We have ions and we have electrons. They'll all interact together. We'll have to sort it out. If I consider the total Hamiltonian, the Schrödinger equation that I would get is unsolvable. So we'll have to deal with it in invoking many approximations. Some of them are obvious, some of them are less obvious. So we'll have to discuss them, particularly the adiabatic approximation, which permits the separation of the electronic and the ionic components. We'll have to deal with something that we have introduced already, the self-consistent or midfield approximation, Hartree, and the corrected one with Hartree-Fock, dealing with whatever correlation energy will be left out, and so dealing somehow with it. And then we'll describe, we'll have a system that at least we have a chance to solve it. Even after having made all of these approximations, we will see that, nope, we cannot solve it. So we'll have to deal with it a little bit by assuming something else. And in particular, we'll have to get to the concept of pseudopotentials. Nowadays, there are beginning to be calculations done without invoking this concept. That is thanks to progress in the development of algorithms that can permit the numerical solution, but mainly hardware, the fact that computers are getting so fast. But still, they're limited to some particular cases. I think that you can go up to carbon. Beyond carbon is still a little bit of an issue. So we'll talk about some simple approximations that you can find in the literature, the time-binding method and the K-P method, which are, K-P actually is a perturbation theory rather than method. Then we'll discuss some qualitative features of the band structure of mainly the FCC, face-center cubic semiconductors. They're mostly, I think that unless you go to nitrides, which are wide bandgap materials that come in a structure which is called Wurtzite, which in addition, I mean, they can come either in FCC or Wurtzite structure, so the zinc blend or Wurtzite. Except for those, I think that most of the semiconductors that people deal with in device physics or device technology engineering area are FCC. So we'll discuss some features of these semiconductors. And then we'll talk about single electron dynamics. I'll talk also about how to calculate band structures using pseudopotentials. If you dare, I can tell you how to write a code, a computer program that actually can calculate the band structure using empirical pseudopotentials. I wouldn't dare do DFT. It's doable, but it's a lot of work. And then maybe somewhere in here, somewhere in between, I would like to show some slides of the talk that I gave some time ago, because it relates to the calculation of the band structure of systems which are called low-dimensional systems. Thin films, like two-dimensional materials, like graphene, stannine, transition metal dichalcogenides, and so on. But also nanowires, nanotubes, how to use, for example, empirical pseudopotentials to do the calculations of that band structure, and what we can learn from there. I think it may be interesting because the amount of research on two-dimensional materials is impressive. Once I had to give a review presentation and started trying to count the number of papers that have come up since the Novozolov and Geim paper on graphene, when was it, 2004. I couldn't. The amazing thing is that the number of journals that have come up since then on two-dimensional materials, not articles, just journals, is impressive. We're in several dozens. And they keep growing. And just the last 2 days, I've received emails notifying about the debut of a couple of new journals, solids and whatever else, materials, I don't remember. So, okay, publication inflation, which one can talk a lot about it. Okay, so that's the idea. Again, this will be the main part, conceptually the main part, and then this will be, if you want, consequences of that. But from an application point of view, this is the interesting thing. But I think that learning the basic physics, which is behind the complications that we have in calculating the band structure materials, why there are still problems, why as I've been feeling for the past couple of years, even density functional theory has a limited predictive power when you're dealing with the conduction bands, particular electron-phonon interaction. That is something that has the roots into what this is coming from. So, crystals. Any question about this thing? Again, I don't hear much of feedback, but please let me know if this is interesting, if this is something that you're interested in. We can always adjust a little bit. For example, I'm not an expert on magnetism. If some of you are interested in magnetic properties, I can do a little bit of work and tell you what I know about magnetic materials, but I've never worked on it. I'm interested in everything, but professionally I've not been interested in it. So let me know if you're interested in something that I will not cover, and I'll do my best to do that. Crystals. What are crystals? Crystals are, this is the basic equation that I want to emphasize. So my analogy usually is you're building a new house and you want to buy tiles for your kitchen floor. So you go to a tile shop and you select the tiles. And let me give you one constraint. You can choose only one type of tiles. You cannot mix and match. So if you use square tiles, you're going to go with squares. So for example, you cannot use octagonal tiles, because with octagonal tiles, you're going to have little square left without any tile cover. So you can choose only, and I think in 2 dimensions, you can have only 5 types of tiles that you can choose. That will be what we call the lattice. Okay, so if you choose square tiles, if you choose rectangular tiles, if you choose rhomboidal tiles, if you use hexagonal tiles, these are the type of tiles that you can use, you can choose to cover your kitchen floor. And this is the lattice. So it's the set translated to 3 dimensions. You can have only 14 types of 3-dimensional tiles. I don't have a better word for it. Mattonelle in 3 dimensioni, whatever. So you can have only 14, and they're called Bravais lattices. And that's the first step that you do when you go to the shop and select your tiles. Then you have to choose the color of the tile or the picture on the tile. There might be a little flower, maybe a little apple, maybe a little bunny, whatever. You have to choose what's in each tile. And in our terminology, this means how many atoms we have in each cell, which is the technical name for the tile that I use, and where they are. So, for example, if I have a cubic lattice like silicon, I will choose a cubic set of tiles. And let's not talk about the primitive cell yet. The basic cubic cell, which is larger than the primitive cell, has 8 atoms. And so you tell me, I want a cubic tile, and I want to put 8 atoms in this cell, which is the design, if you want, of what's in the tile. So the lattice is defined as a set of points such that if I'm sitting at a position R, and then I move to a position R prime, if the difference between these points is a lattice primitive translation lattice vector, I have the same view. So this is something that we may call the periodicity. If I translate my lattice by a particular set of vectors, and I use the symbol big R sub L, L is actually a set of 3 integers. If I translate it by these particular vectors, I have the same picture. Typically for a cubic lattice, if I translate my point in x direction by the length of the side of a square, on a square lattice, then I have the same picture. I can translate along the y direction. In 3 dimensions, I can translate around the z direction by the length of the side of the cube, and I have the same picture, I have the same view, which means it's periodic. In this example that I just said, actually, I can do the translation along 3 directions in 3 dimensions, and the vectors little a, little b, and little c are what we call the primitive or fundamental translation vectors. Okay, so if I translate in a cubic lattice by a vector A, which has component A00, 0, where A is the size of the cube, the length of the cube, this is one primitive translation vectors. B may be the vector 0A0. I'm translating along the y direction. C may be 00A, which is translating along the z direction. So my lattice is defined by these primitive translation vectors. If I tell you what little a, little b, and little c are, I've told you what the lattice is. I've told you everything about the shape of the cell that I have. Okay. So a cell is actually the solid which is spanned by these translation vectors, okay, A, B, and C. So you have these 3 translation vectors and you span them, and that's the cell that you have. So the cell spanned by A, B, and C that I gave you before is just a cube of sides with length A. This clearly is not a unique definition so far, because on a cubic crystal, for example, I can translate by a distance A, where A is the length of the side of the cube in the x direction. I can move by 2A, by 3A, by NA, where N is an integer, and I still have a translation vectors. So it's convenient instead to introduce the primitive, or what is called the Wigner side cells, or the primitive translation vectors, which are the smallest vectors that satisfy this periodic property. Okay. So I can define translation vectors in many ways, but there is only one way in which I can define the smallest possible set of translation vectors, and the cell which is spanned by these primitive translation vectors is called the primitive of the WS, or Wigner side cell. The volume of this cell is given by this expression. You take the outer vector cross product of A and B, then you dot it scalarly with C. The order in which you do this doesn't matter. I hope you know that. You can permute cyclically these things, or even not cyclically. You only change a sign, and that's why I put the absolute value of this. And this is the volume of the cell, which is something that you may want to practice and compute in a few cases, because it may come out handy. So the lattice, to repeat, is the set of all points R prime which are generated by the translation operations. So if I have a cubic lattice, the vertices of the cubes are my lattice points. Okay. If I have an hexagonal lattice, it will be the 6 vertices of the of the hexagon, which are the lattice points, and in a 2D hexagonal lattice. And the translation vectors are just two vectors of with span a degree, an angle of 60 degrees that contain two of these points. Okay. Again, in 3 dimensions, as I told you, if you go to the tile shop and you want to buy your tiles, you cannot choose with the constraint that I gave you, with the rule that I gave you that you cannot mix or match tiles of a different shape. Then you can have only 5 types of tiles. In the solid, you can have 14 types of tiles. Maybe I should have, sorry for my clock, 10 o'clock. Okay, we're done. There is, if you go to the Kittel book that I mentioned at the beginning about one of the suggested readings, it's a undergraduate book, but you can Google it. Look for Bravais lattices on Google. I'm sure you're going to see the pictures of the orthorhombic, the monoclinic, the tetrahedral, whatever, all the types of Bravais lattices that you can have, all the cubic, various types of cubic, body center, face center, and so on. So there are only 14 of them. These are the volumes, elemental volumes that can span the entire space. Exactly the same way there are only 5 types of sets of polygons that can span the entire, can cover the entire plane. Okay, and then you need the basis. And the basis, again, as I told you, is the number of ions that you have in each primitive cell and where they are. So this is defines the crystal or crystal structure. So again, you need 2 things. You can have, for example, a face-centered cubic lattice, but if you don't tell me where the ions are, I don't know what you're talking about. You have to tell me also what is the basis of the ions that you have. In terms of terminology, if you take a plane, an arbitrary plane that intersects the principal axis, not necessarily orthogonal here, remind you, A, B, and C, which are spanned by the direction of these vectors at some distances. These are usually integers of these numbers. These are called the Miller indices of a plane. And if you take the reciprocal, is the way to define the minimum set of integers that can define that particular plane. So the 1, 0, 0 plane on the cubic crystal will be a plane that intersects only the A-axis, for example. The 1, 1, 1 plane will be the plane which is cutting the 1, 1, 1 vector. And so it cuts both the A, B, and C axis at the same distance. This is an example of an FCC lattice. This in particular is the I think it could be gallium arsenide, for example, where the black dots are gallium and the white dots are arsenic, or vice versa. If you take the atoms to be the same, this will be silicon. This is not the primitive cell. This is the cubic cell that contains 8 full atoms. Remember, it looks like there's more than that, but you have only 1/8 of each of these atoms at the vertices, and you have only 1/2 of each atom which is at the center of the face. And so the total number of atoms that you have is 8. The primitive cell, the Wigner side cell of this is this volume shown here, which is spanned by a vector which is 1/2, 1/2 along the XY direction, 1/2, 1/2 along the YZ direction, and 1/2, 1/2 along the XZ directions. Okay, so this is a cell, and actually this is the primitive cell, and this primitive cell actually, if you look at it, contains 2 atoms. If I look and rotate this by 90 degrees along the Z-axis in the counterclockwise direction, this is the picture that I have. So in the primitive cell, I have 2 atoms. So this is the typical, like I say, the battle horse that we'll be talking about for FCC crystals. Okay, good so far? So in the particular case of an FCC lattice, again, I use the word crystal erroneously. I really should have used the word lattice because that's what we're talking about. If I tell you also that I have 2 atoms per unit cell, then yes, then it's a crystal. The typical the primitive translation vectors that we will use for the FCC lattice are given by those vectors that I showed before, sorry, these guys, the A, B, and C, are exactly these three vectors, okay, which are in the figure. Okay, it's not page 66, it's the previous slide. For an FCC, I'm not going to go into group theory. I'm not a great expert on that. We have to do. I know more about continuous group than point groups and discrete groups. But for an FCC crystal, we have essentially 48 symmetry operations, which is called the OH group. Essentially, if you have we'll talk about it when we deal with the Brillouin zone, and I'll tell you why there are 48 symmetry operations. Essentially, they are reflections around many planes that you can have because of the high degree of symmetry. This is highly symmetric, of course. You can reflect it over any of the three planes. You can swap coordinates x and y. You can swap, which gives you already eight different operations and 6 reflections. So you have 48 operations, symmetry operations. Okay, this is an important thing that I want to talk about instead. And that because it leads to the concept of reciprocal space, K-space or whatever. And so the Brillouin zone and the equivalent definitions. Now, here in the very definition of what a crystal looks like, I talk about periodicity. Clearly, this is equivalent to what I said in different terms. I have the same identical view, I say here, when I view it from these 2 points, which are one translated by a lattice vector. Equivalently means that the physical configuration is invariant under a translation by a lattice vector, which means it's periodic. So any physical quantity that I have to deal with has to be periodic. If I have silicon, I want to calculate the electron density that I have in a silicon cell. Clearly, if I translate my charge density to a point which is in an equivalent point in the next cell, so I translate it by a lattice vector, I have to find the same. So any physical quantity, mind you, the wave function is not a physical quantity. So the wave function squared is because it's proportional to the charge, but the wave function itself is not. So the wave function will actually have a phase when I move it by a translation vector. And this is actually the Bloch theorem. So any quantity which is physically meaningful has to have this periodicity property. Okay, let's consider a Fourier transform. As a matter of terminology, I will be sloppy to not pay much attention when I say Fourier transform or Fourier series. It's related to the type of normalization that you use. If you use a finite volume normalization, then you have many wave functions or many states, discrete. If I go to the infinite volume normalization, it becomes a continuum. So the only difference is whether the sum, usually divided by the volume, is equal to an integral divided by 2 pi cube over k. So I will be a little bit sloppy. I apologize. If this creates some confusion, let me know. So this is strictly speaking a Fourier series. I call it Fourier transform because when I want to do calculation, eventually all of this has to become an integral. Otherwise, I don't know what to do with it in most cases, right? Integrals are way easier to calculate than sums, than series. So anyway, so let's take this Fourier transform of this function. These are the coefficients. And these coefficients, big K sub h, I call them like that, I would call them K, it doesn't matter. But I can determine them clearly by, I think it's called the Euler's formula for Fourier series, by simply projecting my function, whatever that is, my density, charge density, into one of the basis vectors of my expansion, which is e to the minus ik, kr. Okay, and I integrate over the volume of the Wigner-side cell because this is the periodicity that I'm dealing with. Very good. So what is strange now? Well, but we know that this function has to be periodic, right? That's what we said. This is the property that we have. So if I write now the Fourier series, Fourier transform, whatever, the Fourier representation, let's be general, of this function, it's exactly what I have here, right? Except that I have to add the translation vectors. To this R, I have to add one of the translation vectors. This must be equal to this. So how can that be? Because this function we saw doesn't have any big R sub L. It's not here. It does. So the only possibility that this can be true is if e to the I kh dot big R sub L is equal to 1. There's the only possibility for which this is true for the function being periodic. So we must have this property, which means that the dot product between this big K and big R has to be n2 pi, a multiple integer of 2 pi. Now, it can easily be seen. I would suggest that you check it by hand and convince yourself that if I define these three vectors, big A, big B, and big C, as 2 pi divided by the what I call V cell before, the volume of the cell, which was here, okay? This is exactly my omega in this slide, okay? 2 pi over omega, and then I take as vector A, the cross product of A and B, for B, the cross product of B and C, for C, the cross product of C and A, little c. These are the primitive translation vectors that we define and that define the lattice. You can actually do similar definition by rotating cyclically. So I could have B cross C, here I could have A cross B, and so on. You get the same stuff, except for a sign, perhaps. If you take these as primitive translation vectors as a new lattice, then you see that these are the lattice points of this new lattice. This is a particularly important lattice, which is called the reciprocal lattice to the original real lattice that I had before. You can go and I would encourage you to do the algebra at least once, if you've never done it before, to make sure that this is true. That really, if you define these vectors big A, big B, big C in this way, you actually satisfy this rule. And the integer n depends clearly on what these integers h1, h2, and 3 will be, and so on. But you always get an integer of 2 pi, okay? This is called the reciprocal lattice. These big A, big B, big C are called the reciprocal lattice vectors. These vectors K sub h are usually called G with a big G and called the G vectors. And when I mention a G vector, I mean a vector of the reciprocal lattice. As for every lattice, there will be a primitive cell, which means selecting the smallest possible translation vectors that I have here. Actually, if you use for a, little b, and little c, the primitive translation vectors, these will be already the smallest possible translation vectors of the reciprocal lattice. And the primitive cell is called the Brillouin zone, or first Brillouin zone of the lattice, okay? FCC lattices usually have a reciprocal lattice, which is a body center cubic, and vice versa. And here I think I have a picture that shows what is the primitive cell in an FCC lattice. So these are 4 Brillouin zones, 4 primitive cells. You see that they fill the entire space, and they have that funny space, the funny shape. They're essentially cube in which you have cut from the 1, 1, 1 plane all the corners out. And you see that these are the cube. These little squares that I have at the edges are the faces, only faces of the bigger cube. But then I went with a big knife and chop off big sections of the volume of the cube with a plane which is perpendicular to the 1, 1, 1 direction. We will mention later, we'll use later this terminology, which is a point group symmetry notations of what these particular points are in a Brillouin zone. There are points in which the symmetry is particularly high. For example, at the center of the Brillouin zone, you have lots of symmetry. If you go very close to the center, it's almost spherically symmetric. This is called the gamma point. And then we will mention what the other X and L and K and W and U points are and how they refer to the band structure of the solids. Okay. Are we good so far? Am I still online? Can you hear me? Occasionally, I would like to get confirmation that I exist.
Yes, Professor, we can hear
Good.
you.
Thank you. I appreciate, because again, as I told you many times, I am always dreadful of the idea of having spent half an hour talking to myself. Good. Okay. one important property that I said before is, if you remember when we were talking about this stuff, I said any physical quantity has to be periodic. A wave function is not physical. You cannot measure the wave function. You can measure the square of the wave function. Indeed, it has been measured, like famous quantum chorale that have been seen by, I think, by people at IBM Almaden early on in the 90s even. Anyway, so the wave function doesn't have to be periodic. However, it has to be periodic up to a phase, because I want the square of the wave function to be periodic. So there is a famous theorem, which is the Bloch's theorem, that of course we will use a lot, because it will be the starting point for any calculation that we do about the electronic properties of a crystal. The wave function has to be such that when I translate it from a point R to another point by translating it by a lattice vector, I only gain a phase. The phase has to be of this form. This would be e to the I alpha in general, where alpha could be any phase. The phase has to be the dot product of a k vector times the translation vector, some vector times the translation vectors. This follows from group theory, the property of translations in this periodic system. So this is an important property, because it says that the wave function, if you translate it, this is equivalent. It says that the wave function has to be periodic up to a phase which is a plane wave. And this is the famous Bloch's theorem. So this function u is really periodic. And this is just a phase. You realize that if I take psi square, I get this goes away, becomes 1, so I get just the square of u. And indeed, this shows that I maintain, I satisfy my requirement, a physical requirement of the fact that the square of the wave function has to be periodic. Okay, this is a little bit of an explanation of why the phase has to be of this form. The important thing is that indeed that's another way of showing it, that the wave function has to be periodic. So this is an extremely important theorem, because in practice, so I'm going to be a little bit sloppy here, but in practice, in most applications, the electrons that we will be dealing with in transport, consider an electron device, electrons in silicon, they will be close to the bottom of the conduction band. Although, strictly speaking, I shouldn't mention these things yet because we have not dealt with them, but I assume that you know what I'm saying, what I'm talking about. So the electrons will not be moving too far away under some conditions, not very high fields and so on, away from a particular region in the Brillouin zone, which is where the minimum of the conduction band is. So this function can be considered roughly to be a constant. And by the way, these functions are the remnants of the atomic orbitals that you're dealing with. Tight binding actually is a method in which this is seen explicitly, but it actually is made use of explicitly. But these are the remnants of the atomic orbitals. And these are essentially plane waves. So if I can ignore variations of this portion of the wave functions when I'm dealing with my transport calculations, I essentially deal with free electrons in free space. The entire complications which is due to the crystal disappears, as long as I know how to accelerate the electrons and how fast they go. And that is something that we will deal at the end of this section. We will talk about single electron dynamics, talking about the acceleration theorems, two major acceleration theorems that are huge simplifications in dealing with transport problems. So for now, let's keep it in mind. It will be a huge simplifications of our problem to be able to express the wave functions in this form. Beginning to run out of voice here. Okay, why this particular property? I don't know if you remember what Bragg reflections are. You have a lattice. I don't know, let me show the lattice of these points, for example, just to have a picture. You're coming in with a plane wave. Each plane wave is scattered by this central point, each of these points, and then the wave that propagates clearly results from a superposition of all of the waves which are scattered from all of the lattice points. And you know that there are some particular conditions that say, whoops, where am I? Here, that says that the waves will be completely reflected or completely transmitted. And this condition is related clearly to the wavelengths that I'm shining of the wave that I'm hitting the crystal with, and clearly the lattice configuration, which is this reciprocal wave vectors. So when this condition is satisfied, you can see that actually have a strong reflections, and the wave is completely reflected. And this is the physical reason why this condition comes up when we're dealing with Fourier transforms of physical quantities that have to be periodic in the periodicity of the lattice. Okay. If you're okay with it, I would stop here because for today, I would like to hear from you occasionally, asking questions, particularly if you go into material that you might have not seen before. It will be important if you slow me down. Remote teaching is not my favorite. To do it now is the third semester. I really don't like it because I tend to go too fast. I realize. I'm an old-fashioned guy. I like whiteboards or blackboards. I even had blackboards a few years ago with chalk, and you go much slower, and you write the equations, you develop them on the whiteboard or blackboard, and I think it's much clearer. You also make mistakes, so students can also see what kind of mistakes one can make. Here with slides, I tend to go too fast. So if you interject, ask me questions, I would appreciate very much, because I assume particularly now when we'll go and deal with what I have to do, starting from block theory and then write this messy Hamiltonian for the total crystal, there will be questions, and there are a lot of very subtle issues about the approximations that we will make. And I assume that it will not be completely transparent and crystal clear, pun intended, in this particular situation. So please ask me questions, give me some feedback. I would like to hear from you. Send me an email if you wish. Am I going too fast? Am I going too slow? Is the material of interest? Do you understand my broken Italian New Yorker English? So let me know these kind of things. Okay? So today I would stop here. On next Thursday, we'll start with what I think is the major part of the class. I'm going too fast because usually I don't get here that quickly in 2 lectures. Well, maybe 2.5 because we're longer lectures than I'm used to. But so is that okay with you? How are we doing here?
Yes, Professor, I have a question actually.
Oh, good.
It's not strictly related to the things that you've discussed in the class.
Yes.
It was just to know, if it's not against your policies with classes, if we can have the slides in advance, so we can maybe print them and look at them before the class.
So I posted somewhere these lectures notes, right? And I'm following them. So if you wish, I had prepared actually slides for the next few lectures. So you would like to have them in advance?
Yeah, if it's possible.
Okay, so you can look at those notes, but I will post the slides. The problem, I never know exactly when I will stop the lectures, so they may change, but I will post in the, what is it called? Annunci, I guess. I forget what it's called, or I will post the slides. I think I've posted the slides of the last lectures already.
Yes.
So I will do it. I will do it for the slides of next week. And again, remind me if I don't do it. If I don't do it in the right time, remind me. I tend to forget my age. Okay. All right. Thank you for this suggestion. Any question? Any technical question about this? Are we doing okay?
No, Professor. Thank you.
Okay. Then have a good weekend. And I hope that everybody will be in next Thursday. And I hope that you're enjoying what we're doing here. All right. Goodbye.
Bye, Professor.
Thank you.